Hello guys, so welcome again to another lecture. In this lecture, we're going to continue talking about the arithmetic operation in x86. Last time we discussed the addition, the subtraction, and now it's a turn to the, multiplication and division. So let's start by the multiplication. So to multiply two numbers in x86 processor, or, the newer versions of it, we use four registers. We use AX, AL, AH, and DX. We're gonna see how we're gonna use these registers, okay? And we have three multiplication cases. We can, multiply two numbers, each one is 1 byte, so byte times byte, or two numbers, each one is word, so word times word, or two numbers or two variables, and one of them is a byte size and the other one is a word size. Okay. So let's start by the byte by byte multiplication. Okay. So in that case, one of the operands, one of the numbers that you want to multiply must be in AL register. And the second one can be a register, any register, or in memory. Okay, much more general. And after the multiplication, the result will be in AX. So once you do the mul is our, instruction here that do the multiplication. One of the operand in AL is the other one in register or in memory, and the result will be automatically go to AX. AX means here AL and AH together. AL or AH, AL. Okay, and that's expected because when you multiply, a byte variable by a byte variable, the result will be more than a byte in general, of course. Okay. So here, for example, you have, a variable called the result, okay, which is a word, define word, and it doesn't have initial value. And you move here 25 hexadecimal to AL. So this will be one of the operands. And the second operand that you want to multiply with is 65H, and you store it in BL. Then you write mul BL. Look here, we don't have two. This structure called mul doesn't have two operands, just one operand, because by default, the other operand will be in one of the registers that we talked about, AL, AH, AX, and the DX. In that case, since we are multiplying byte by byte, so it will be detected by the processor that, one of the operand is 1 byte. So the other operand should be also 1 byte, which is AL. So that's exactly equal to, or, equivalent to saying AL equal to 25, times 65, of course, hexadecimal, both are hexadecimal. Okay. Afterwards, you can, of course, move the result into, the result variable here. Okay. And this is, by the way, AX, AX here, not AL. So AX equal to 25 hexadecimal multiplied by 65 hexadecimal. The result will go to AX, and then you can move, for example, AX to, it's, of course, it's not mandatory, but, if your program requires this, then, or your application, then you should move, X to another variable, whatever. Good. And of course, here you use register addressing mode. So this, when the second operand is a register, then, this is a register addressing mode. The second case is multiplying two variables, each one is word size. So here, since we are using word, we cannot use AL anymore. So in that case, we're going to use AX. So one operand will be AX by default. The second operand can be a register, any register, or it can be in the memory. So here is, an example for this. We have three variables. One is called data3, and it has this number in hexadecimal, which is, of course, word. Another variable called data4, and it has this value, which again word. and we want to multiply them and store the result in a memory location or a variable called result1, which is also a word. Okay. So in that case, we move data 3 to AX. This is a must, and then the second, then you can say that just mul. And in that case, the value in data 4, the variable data 4 will be multiplied by X. And, the processor automatically, will recognize that since one of the operand is word, so the second one should be word AX, and it will multiply them by each other and store the result. And this is what we missed to say, in AX and DX together. So when you multiply word by word, the output might be, 2 words. So the size of the output should be, can be 2 words, up to 2 words. So we need 2 words to store the result. So that's why we used AX and DX here. So AX will have the lower word and DX will have the higher word. Okay, so the result here of multiplying data 3 by data 4 will be stored in AX and DX. Since we want to, store the final result in the result1 variable, then you can move AX to, the first, 2 bytes of result1, then, store the second or the higher, or the higher word, which is in DX, in the higher word of result1. Result1 here is of word size. It has 2 locations. It's an array. Each array location is of word size, and it's dob, or duplicate. Question mark means don't initialize these 2 locations. The first location is, or the address of the first location is pointed to by result1 itself. The address of the second location, which is 2 bytes further, should be result+2, result1 plus 2. So it's like you have 4 locations. This is result1. So the first 2 locations is of type word. That's why it are 2 locations, and we point to the first byte of them using result1 itself. Then the second 2 locations here, we refer to the first location by result1 plus 2, because we go 2 locations further. Okay. The third type of multiplication is when you multiply word times byte. So one operand here will be in AL, and AH must be 0. So in that case here, AH must be 0. That's, otherwise there will be an error. So here, since the 2 operands are different in sizes, okay, so to differentiate between word byte, so that for the processor to be able to differentiate between the different 3 cases, in that case, word by byte, H must be set to 0. And the second operand can be in a register or in a memory. Okay. So let's take an example again here. So we have 3 variables, data 5, data 6, and result 3. Data 5 is of type just 1 byte. 6B, this is 8 bits, 1 byte. Data 6 is of size word, and this is of course word. This is a value 12C38 hexadecimal, and you want to multiply them and store the result in result 3. And again, the result here will be in AX DX, and again AX will take the lower or the least significant word, and the x will take the high or the highest or the the most significant word, both together. Okay, so let's see. So the first instruction here, move data 5 and AL. So this is the byte, and we should clear or set AH to 0. One of the ways is to subtract AH from itself. You can also say move AH and 0. That's also okay. Then you make the multiplication. So mul data 6. So that means multiply data 6, which is that number here, by AL. And the result, as we said, will be in DX, the highest or the most significant word, and the least significant word will be in AX here. Okay, so to store the output in result 3, what we do is do the following. First, we move the address of result 3 to be X. Then we move AX to the first location, BX. Then we add 2 and move DX to the second location, because the second location is 2 bytes further from the first location. Because result 3 is an array. This array has 2 locations. Each location is of type word. Good. Here is now a summary of all the multiplications operations, which are basically 3. This is a summary of operand 1, operand 2, and the type of results that you have. So for byte by byte, we said that the first operand should be in AL. The second operand can be registered on memory, and the result will be in AX. The second type of multiplication will multiply word by word. The first operand should be in AX. Again, operand 2 should be can be a register or a memory, and the output will be DX AX. Again, the output can be of size 2 words together, 32 bits. So we need 2 registers to store this result. So we're gonna use 2 registers at the same time, DX and AX. DX will take the most significant word, AX will take the least significant word. Finally, when you multiply word by byte, here, since they are different, then the first operand should be in AL, and to differentiate, AH must be 0 to differentiate between this case and the other 2 cases. So AH must be 0. The second operand can be a register or memory, and again the output would be in DX and AX. Okay. So, and one final note here: if you have a word by byte multiplication and you didn't clear AH, then the processor might think you wanna multiply 2 words together. A word is the second type here. So instead of multiplying AL by the second operand, it will multiply AX, which is AH, AL together, by a second operand. And that's why you must clear AH, must be cleared or set to 0. Because if you didn't set it to 0, its value will be included in the operation. And that will be an error for you. Logical error, of course. Good. Now the second, arithmetic operation in that lecture, which is division. So division is very similar to to multiplication, and we use for it the div instruction. And again we're gonna use the same 4 registers, AX, AL, AH, and DX, just like multiplication. But now there are 4 different cases for divisions. You can divide 2 variables, each one is 1 byte. 2 variables, each one is word. 2 variables, again, one of them is word, the other is byte. And finally, two variables. One of them is double word and the other one is word. Okay. There are also some special cases for the division, that the processor should take care of. When you have, an error in your division. So, for example, if you divide by 0, or if the quotient, is 2, the quotient when you divide the two stuff, like for example, 5 divided by 2. So this operation has the following result: 2. So there are two 2's basically in 5, and there will be a remainder of 1. So 2 is the quotient here. It's called the quotient, and 1 is the remainder. Another is 7, for example, by 3. Again, there are two 3's in the 7. So here is a quotient. So the output here is 2, and the remainder is 1. So 2 again is the quotient, and 1 is the remainder. Okay. So if the quotient is too large for the assigned, register, then again this is an error. So in two cases, the CPU, the x86, will basically will give what's called interrupt or exception error, and that's to notify the user or the programmer that you have an error here. You either divide it by 0, or the register that should contain the quotient of the operation is not enough. The size of it is not enough, for the quotient. The quotient need, for example, you're gonna store the result in AH, for example, but and the H is 8 bits, is basically 1 byte, but the output is, for example, needs more than 1 byte. Like for example, 140. 140 is 9 bits. So 8 bits is not enough for it. So let's, explore the first, type of division, which is when you divide byte over byte. So you have here two variables. You want to divide by each other. Each one is 1 byte. So the numerator of this operation will be in AL. This is just similar to what we take in multiplication, in which the first operand should be in AL. Here the numerator should be in AL. H must be set to 0. And the denominator can be, either a register or a memory location, but it cannot be immediate. So for example, here, if you want to divide 95 over 10, okay? So this is, a buggy, we can say, or illegal, way to do it, in which you put, the 95, which is in data 7, into AL, and then you clear AH, like what we said. Then you say div 10. That's incorrect. So there will be exception error here. Okay, so how to do it? So there are many ways. So first, using direct mode. So instead of saying div 10, no, you say div data 8. So same start, we put the 95 in AL, the numerator. Then we clear AH. Then you say div, data 8. So the, the x86 here, or the processor, will basically, divide 95, over 10, and the 10 is stored in data 8. And the quotient will go to AL, and the remainder will go to H. So that's very important to know here. So when you divide byte by byte, so the quotient of the operation goes to AL, and the remainder will go to age. So in that case, there are two variables called quotient one and remainder one. Each one is 1 byte. So, and we want to move the result of the operation or store the result of the operation, this division operation, into this quotient and the remainder variable. So we move AL to quotient one and we move AH to remainder one. Of course, again, this is not mandatory, but if your application needs to use a separate variable or a memory location to store the outputs, then you should do this, something like this. This is another type of of byte. This is another way to do a byte over byte division, in which you do the register addressing mode. So what we do here basically is we put the value of the denominator into a register, and in that case it's BH. Then you say div BH. It's exactly the same. And again, a third way to do it, is also exactly the same here. But this is register indirect addressing, in which you put the the address of the the variable data 8 into a register. So move bx offset data 8. So here we move the address of data 8 variable or memory location basically to bx. Then you make the division, and since bx itself doesn't have the value, which is 10, but it has the memory location of this variable data 8, which contains the 10, then you say byte pointer bx. And we explored this type of operation before in our previous lectures. Then after this division, again the quotient will be in AX, and the remainder will be in DX. The second operation is word divided by word. So when we divide the word by word, so we need of course a register which is at least 16 bits or one word to store the numerator. So in that case we're going to use AX. DX here must be cleared. The denominator can be a register or memory, and again it cannot be immediate, like what we explored in our first slide about the division. And after the division, AX will have the quotient and the remainder will be in DX. That's an example here. So you're gonna divide 150 over 100. So in that case, of course, here the quotient is is 100 and the remainder is 50. That's the quotient, that's the remainder. So first you move the numerator, which is 10050 to AX, then you clear DX, then you move 100 to BX, and you say div BX. So automatically, the processor will take, the 150 here and divide it by 100, and put the quotient in AX and the remainder into DX. Good. A third type is word over byte. So again, the numerator here should be 16-bit. That's why we use AX. And again, the denominator can be a register or a memory. After the division here, AL will contain the quotient, AH will take the remainder. Example, if we want to divide 2055 over 100, so let's do it. 2055 over 100, this will have 20, and the remainder will be 55. So that will be the quotient, that will be the remainder. So we move the numerator 55 into X. We move the denominator here to CL. You can use any register. And we say div CL. So automatically, the processor will divide the 55 over 100. The value inside is CL. Then the quotient, will be in AL, and the remainder will be in H. And of course, you can store this quotient and this remainder into some memory locations. The final, type of division is when you divide a double word variable over a word. Double word means more than 16 bits. We need here two words, 32 bits basically. So the numerator here now will be in AX and DX together. The most significant word will be in DX, the least significant word will be in AX. And the denominator can be again a register or a memory as usual. And after the division, the quotient will be in AX, the remainder will be in DX. And one must say here is that if the quotient is more than, needs more than 16 bits, there will be an error. Because remember here the quotient will be stored in AX, and the X is only 16 bits. So if the quotient of that operation is more than 16 bits, AX will be not enough for it, and that will be like an error for you. So there will be an exception, so that that the result of this division is not quite right. Here is an example. We want to divide data 1, which is what this number 104,432, by that number. The first one is double word, define double word, and the second one is just a word, define word here. And you want to put the quotient in in a quotient, in this variable, and the remainder in this variable. So first we move, AX, we move data 1, I'm sorry, to AX. But since data 1 is double word and the X is only one word, you said word pointer. So that means take the first, or that means, take one word of data 1. Which word of them? The one pointed to by data 1. So data 1 is double word. So 2 words basically. So you have here 2 words, this word and that word. The address of the first one is that location, the address of that location, and the address of that location, or the second double word, is that location. So in the address of the first one is pointed to by data 1. The address of the second one is data 1 plus 2. That's why here we said move data, move dx word pointer data 1 plus 2. Take the higher word and put it in dx. Then you say div data 2. So the quotient will go to AX and the remainder will go to DX. That's finally a summary for the division operation. You have here 4 division operations. when you divide byte by byte, the numerator should be in AL and the H should be cleared. Again, the denominator should be in a register or a memory. It can't be immediate. And the quotient and the remainder should be in L and AH respectively. When you divide word by word, so X will have this word, the numerator. The X should be 0. The denominator should be a register or memory. The output is the quotient of the output should be in X, and the remainder should be in DX. When you divide word by byte, you know, X should have this word. The denominator should be a register or a memory. The output quotient will be in AL. The remainder should be in AH. When you divide double word by word, so the double word will be in DX, X together, 2 registers at the same time. The denominator should be a register or a memory. And again, the output, you know, is quotient will be in AX, and the output remainder should be in DX. And remember here, if you needed more, if the quotient need more than 8 bits in that case or that case, or more than 16 bits in that case, then you will have, you know, an exception error. So the processor will raise an error for you that's saying, hey, you need more than you need more size for this quotient. And again, in general, whatever you do, if you divide by 0, this is another type of error that might be raised during division. That's it, guys, for the division and the multiplication. Thank you very much for watching, and see you in the next video. Bye-bye.